me. In this lesson, we're going to look at drawing dilations. In the last video, we looked at identifying what makes a dilation. And in this case, we're going to actually make our own. What we're going to look at, we're going to focus on is drawing a dilation for two-dimensional and three-dimensional objects. The outcomes we're going to cover are: draw with or without technology a dilation image for a given two-dimensional shape or three-dimensional object, and explain how the original two-dimensional shape or three-dimensional object and its image are proportional. Identify and describe the applications of transformations in construction, industrial, commercial, domestic, and artistic contexts. Solve a contextual problem that involves transformations. Making dilations is easy if you have a computer, a tablet, or a smartphone. Usually with your tablet or smartphone, it's simply a matter of either to make something get bigger, touch your screen with your forefinger and your thumb close together and spread them out. Or if you want to make something smaller, you can start with your fingers spread out on the screen and bring them together. And that will make something get bigger or smaller. So that's zooming in. That is making dilations. The same image but in different sizes. So for any of these, we can use the zoom feature. I can use my zoom feature to make my my object much bigger, or I can use my zoom feature to make my object much smaller than I started with. In both cases, my image is a different size, but the same has the same characteristics as the original object. So it has the same proportions. So we're going to look at drawing dilations. Logan is entering his band, the Arrows, in a Battle of the Bands contest. He's creating a flyer to advertise the contest. He wants to include the band's logo, but he needs to draw it twice as big on the flyer. How can Logan check that his image is proportional? Okay, so we're going to look at two different methods for making dilation of an object, in this case the logo. The first is to actually measure it out using a ruler. This is already dilated a bit, but the diagram shows that if we put a ruler on it, that part of the diagram is 1 centimeter from the middle to the end of each line. So from the middle to the end there is 1 centimeter. From the middle to the end of this line is also 1 centimeter. And my arrowheads, the two pieces that make up my arrowhead, are 0.3 centimeters each. That would be the same here and here. Okay, so if we want to double that diagram, we're going to have to increase all the lengths by a scale factor of 2. Recall from our last video that a scale factor is whatever the number is that we multiply all of our dimensions by to get our new image. Okay, in this case we're doubling everything, so we multiply everything by a factor of 2. So I take the 1 centimeter lines and I multiply them by 2, going to make them 2 centimeters. If I take the 0.3 centimeter lines and I multiply them by 2, I'm going to get 0.6 centimeters. So here is my diagram with everything scaled up by a factor of 2. So my new lines from the top of my vertical line to the middle, that's now 2 centimeters instead of 1 centimeter. And from the middle of my diagram to the end, right here, that's going to be 2 centimeters instead of 1 centimeter. And now my arrowheads, the ones that are pointing out, and the ones that are pointing in, right here and here, they're each 0.6 centimeters in length. So everything is doubled from what it was initially. The second method we're going to try is to actually trace the original logo onto centimeter grid paper. Now I say centimeter grid paper here, but it doesn't really matter the size. We're just going to make sure that whatever we do, we're going to double it up later. So we're put it on grid paper, and it looks something like this. Notice also that I've labeled the angles angle A, which is clearly a 90-degree angle, angle B, which is between the horizontal line and the arrowhead pointing outwards, and angle C, which is between the vertical line and the arrowhead pointing inwards. To reproduce this, we're going to use 2 centimeter grid paper. So in the last diagram, from the middle to one of the lines, the ends of one of the lines, I should say, was 1 centimeter. So it went from one grid line to the next. Well, we're going to go from one grid line to the next again, but this time the gap between each of our grid lines is going to be 2 centimeters. So it's going to look like this. And also notice that once again I have my angles labeled. Angle D is 90 degrees this time. Angle E is between my horizontal line and the arrowhead pointing outwards. And angle F is between the vertical line and the arrowhead pointing inwards. So we've made dilation in both cases, but we wanted to check that everything is proportional. So to make sure that the image is a dilation, you should check the angles as well as the side lengths that we've already confirmed using a protractor to make sure that they're equal. And I've put a protractor on my image and on my object, and I found that first angle A is equal to 90 degrees, but we also said that angle D is equal to 90 degrees. And they are corresponding parts in the object and the image. So angle A and angle D are both 90 degrees. They're fine. I also found that angle B was equal to 45 in the original object, and angle E was 45 degrees in the image. So they're equal to each other, and they're also corresponding parts in between the two different objects, the object and the image. And lastly, angle C I found to be 135 degrees in the first diagram. And I found angle F, which was the corresponding angle in the second diagram, the image. I found them both to be 135 degrees. So that means that all my angles are the same in my object and in the image. So because of this, we know that the sides are proportional because we've doubled everything. So we know that the ratio from side to side is going to be 2. And we now know that the angles are the same. And they're the requirements for confirming that something is a dilation. The image is a dilation because corresponding sides are proportional and the corresponding angles are equal. So we always have to make sure that not only are the sides equal, but that the angles between them are equal as well. Now we're going to look at a three-dimensional object. Logan also wants to include this three-dimensional drawing of an amplifier on the flyer. He needs to reduce the dimensions to half their length. How can Logan reduce the dimensions? Well, this is a two-dimensional representation of a three-dimensional object because it's on a flat piece of paper. And to draw these properly, we're going to use a special kind of dot paper. It's called isometric. So this is a two-dimensional representation of the three-dimensional object using isometric paper. I've just gone and traced the original object onto the dot paper. And you can see that the dots are kind of offset from each other. So they don't form an up and down, left, right grid, but they actually form what looks like diagonal lines on the grid. And that helps us to draw three-dimensional objects. So the dimensions for the object here, the length is 6, the width is 4, and the depth is 2. And the side lengths, I got those numbers by measuring the distance between the dots. So if I look at the depth, here's my first dot right here, and there are 1, 2 dots to get to the back of that diagram. So it's 2 units in depth, 4 units in height, and 6 units in length. So to reduce all of our dimensions, we have to multiply by 1/2 because the scale factor in this example is 1/2. So I multiply all of my dimensions by 1/2. 2 times 1/2 will give me 1. So the depth of my image is going to be 1 unit. 4 times 1/2 is equal to 2. So that means the height of my new image is going to be 2 units. And 6 times 1/2 is equal to 3. So the length of my new image is going to be 3 rather than 6. So using isometric dot paper, I'm going to do the same diagram but in a smaller size. So we can see that here. The depth now has a measure of 1 unit. My height of my diagram has a measure of 2 units. And the length of my diagram now has a measure of 3 units as opposed to 6, 4, and 2 as they were before. So this image is a dilation. The angles haven't changed because we're using the exact same isometric dot paper. So the angles between dots is not going to be any different, which means that the angles from our object to our image are not going to be any different. And all of our sides are now 1/2 what they were before. This means that we do have a dilation. Okay, so to summarize, when we have dilations, they have the same angle measures. So the corresponding angles from the object to the image are going to be exactly the same. They also have equal side length ratios, or they're proportional. So if we do the ratio of corresponding sides, for instance, if we have a rectangle, we measure the ratio of the length of the object to the length of the image, and the width of the object to the width of the image, then those values should be exactly the same. And with the ratio actually gives us a scale factor as well. And there's 2 ways we looked at for making dilations, drawing dilations. The first is using a ruler and a protractor. The ruler is used to measure the side lengths, and then once we multiply by our scale factor to draw in the new side lengths of appropriate length. And we're going to use a protractor to make sure that all of our angles are equal from our image, so from our object to our image. Because we also mentioned in the last video that dilations are similar objects. They're the exact same shape but in varying sizes. Of course, we can use a ruler and a protractor, but another way that we could draw dilations is using grid paper for 2-dimensional drawings, which we did see, or possibly isometric paper for 3-dimensional drawings. It's very difficult to draw a 3-dimensional object in 2 dimensions, but isometric dot paper gives us an opportunity to give a very good approximation, and we can use our powers of perception to realize the perspective in the picture.